record onto this computer. So this would be our dihybrid cross up here. And we're going to have different expected values from that. Our expected values will follow the 9 to 3 to 3 to 1 ratio. Let's make an equal sign. That'll follow our 9 to 3 to 3 to 1 ratio. Our test cross with a dihybrid, we're still going to have our dihybrid. I want to make this not bold. And we'll still have our dihybrid, but we're going to cross it with a tester, which will be the homozygous recessive. Our tester will always be homozygous recessive. And this will be our dihybrid test cross. And our expected ratios from this will be 1 to 1 to 1 to 1. And we can go ahead and go through the Punnett squares as to why exactly that is. Or we can, for the sake of time, just proceed with doing the calculation. So we're given our values. We have 225, let's say, these are our observed values. This will be the big A, big B, to 180 of big A, little b, 195 of little a, big B, and 200. Oops. 200 of our little a, little b. And we expect these all to be roughly in the same proportions. Now we're going to calculate our expected values. Let's go ahead and I see. Our expected values is going to equal our total progeny divided by our number of groups, or let's say phenotypes. So that's going to be 800 divided by 4 for 200 expected in each group. So our expected is going to be 200, 200, 200, and 200. So then we want to calculate out the difference, or really the square of the difference. Sometimes I see this as observed minus expected. It could be expected minus observed. It doesn't really matter because we're going to square the results either way, so it's going to come out the same either way. And this is going to be 25 squared, so 225 squared is what? It's 625 actually. This is going to be 420 squared, so 400. This will be 5 squared, so 25. And this will just be 0. And by all means, feel free to stop me if I'm starting to get ahead of you. We're then going to take that value and we are going to divide it by, and in this case, we do care. I'm going to put that in brackets. In this case, we do care what we're putting on the bottom. What we're putting on the bottom is specifically the expected. And if we divide 625 by 200, we get roughly what? 3.1? I'm going to go ahead and round that off. 400 divided by 200 should be 2. 25 divided by 200 is going to be, let's say, 1. 1.25, if I'm not mistaken. This is also probably technically 1.25. And 0 divided by 200 is 0. So those are the values that we generate. And then in order to calculate our chi-squared, we are going to take those values and we are going to add them up. Why are you giving me black? 3.125 plus 2 plus 0.125 plus 0 for good measure. And we're going to get 5.25. And that will be equal to our, we'll just make this italicized, chi-squared, or this is Word, I don't have to be that. I don't have to do that. So our chi-squared value. Once we have our chi-squared value, what we're going to do is we're going to compare it to a table that we had in our lecture. Why don't I go ahead and bring up that lecture really quick? So that should be in several of our lectures now. We're going to compare that to this table. Now, this table is a table that you should be given on an exam or quiz if you need to use it. So you don't have to worry about memorizing this table. But if we look at this table, we need to know two things. One, we need to know our chi-squared value. We also need to know our degrees of freedom. There we go. Freedom. And our degrees of freedom is going to be equal to the number of phenotypes we have, or if we were applying chi-squared tests more generally, we would say the number of groups. But in these cases, we can say the number of phenotypes minus 1. So in this case, this is going to be 3. So our degrees of freedom are 3. And we're going to take a look at our chart here. We're going to come down till we have 3 degrees of freedom, and we're going to look for a range where our chi-squared falls into. So our chi-squared falls into between this 2.366 and this 6.251, and therefore our p-value is going to be between 0.5 and 0.1. So we would say that our final p-value equals between 0.1, or really we can say our p-value is between 0.1, so greater than p-value. P-value is between 0.1 and 0.5. So our p-value is somewhere in there. And our p-value, I'm going to make this one of the definitions on our next worksheet. Our p-value can be interpreted as the probability, the likelihood that our expected is equal to our observed given the progeny counts. That is, in this context, what this p-value means. So it is the probability that our observed values here are statistically identical to our expected values given these values. And so what we're saying is that there is between a 10% chance and a 50% chance that we can claim that this matches our expected values. in which case we would assume that this is in fact segregating, that these are independently assorting. So we would say that yes, our observed are close enough to being equal to our expected. If they were too far different, then our p-value would end up being much lower. And if it's below 0.05, then we assume that the two groups are different. And again, we would work out this problem exactly the same up here, except our expected values will be very different. They won't all be equal to each other. They will have that 9:3 to 3:1 ratio. But that is going to depend on if you're looking at a test cross or a dihybrid cross. So it's very important in these kinds of questions to look for that. Any questions on this?
No, that was pretty like straightforward for math.
Mm-hmm.
Okay. All right. Well, that's